All right, we're good to go. Good morning. All right, small group today. Last week of classes. Can you guys believe it? Well, unless you have Monday classes. I got a class on Monday. But last week for us. So we're going to work through the rest of trigonometry, and then on Thursday we'll probably have to wrap up a little bit. And then I'll give you kind of an idea of the outline for the final exam. So we'll hold off on that until Thursday. But let's get to it. Okay, so just as a little bit of review, my iPad's back in action, feels good. But I had to restore everything. And for some reason, I think the notes weren't backed up or anything. The last note I have is from September 15th, so that doesn't help me very much. But I posted these Trigonometric Part 2 notes on Moodle, so if you want to have those to follow along, that's good. First thing I want to talk about here, I have this little kind of reminder. Recall the definition of the trig functions. So I'm going to use that as part of our review. And I also pulled in the fundamental identities from last day. So because I didn't have my iPad, so I didn't have access to all these, but so now I'm just putting them in the notes so that we have them, so we don't have to write them out a bunch of times. Okay. So for our review, okay, I'll move this one down until we talk about it. So we've got these trig functions. You probably remember SOHCAHTOA, things like that. That's going to come up again today. So we've got sine, cosine, tangent. Those are our go-tos, right? So the top row is kind of our main events, right? And then we've got cosecant, secant, and cotangent. Just the inverse sign, right? So not the inverse function, but the inverse of sine. So y, 1 over y. 1 over x is secant, and x over y, which is just the reverse of tangent, is the cotangent. Okay, notice that there are restrictions as soon as we have some sort of division, right? We have restrictions on the domain. So of course in tangent, we can't have x equal to 0, right? And x traces back to the cos of t, and we're especially going to use these two properties today. Okay. Today, we will use the fact that sine t equals y and cos t equals x. We're going to use that a lot. Okay, so that's something to kind of remember. Or if you want to talk about just kind of, so x, y is going to be cos t sine t, if you want to think about it as an ordered pair. Okay. We also talked about the fundamental identities, right? So the first 3 we use to be able to use our calculator to find cosecant, secant, and cotangent, right? Because we only have buttons for sine, cosine, and tangent. So we need to be able to rework the buttons in quotes that we don't have in terms of the buttons that we do have, right? So here, use these identities to solve for cosecant, secant and cotangent. I realized that I probably just assumed that you knew what those were, and I think that's pretty fair. But I did realize I should probably tell you how to say these. So CSC is cosecant, SEC is secant, and COT is cotangent. Okay. We've also got these additional identities, right? That the tangent is sine over cosine. Fine. Okay, that's linking back to here. If y is sine and x is cosine, then of course y over x is sine over cosine. Fair enough. We can do a little switcheroo here, right? So then the cotangent, which is x over y, well, then we just reverse. So then we have cos over sine. Okay? So these, all of these reciprocal identities come from the top here, so they're definitely related. We've just swapped out x's and y's for cosine and sine. The Pythagorean identities are more useful than you think, right? So if you have to kind of morph a function, then the Pythagorean identities you can kind of look and see. And here, so tangent is related to secant, cotangent is related to cosecant, and then sine squared plus cos squared is 1. That's an identity that we use quite a bit. So we can use these, right, all these fundamental identities to rework functions to something that we might want. And it totally depends on the situation. I know that's not helpful, but we looked at an example last day where we had to re-express something in terms of cosine. I went to go look at the notes. I don't have the notes, so just flip back through your notes. And I think it involved some sort of tangent, and we had to rewrite it as in terms of cosine. Anyways, so that's kind of where we got to last day. Maybe I'll make a note here. We can use the fundamental identities to solve or rewrite a trig function. Oops. Said trig, but I wrote tig. A trig function. Okay. So having these, you obviously don't need to memorize all of these, but having them on hand is going to be really useful. Okay. So let's see here. So the notes I posted, I called it Trigonometry Part 2. What I'm going to do is I'm going to retroactively go in and just pull the ones. So just how we had this, we pulled in this little guy, for example. I'll just arrange those so you don't have to write them out every time so that you have them kind of compiled, but I'll do that later today. Okay, so of course we knew it was happening. Now we look at the graphs of trig functions. So trigonometric graphs, specifically we're going to focus on sine and cosine. If we have time, we might go on to things like the graph of tangent or cotangent or whatever. But a lot of these you can just use Desmos to graph, right? So, but we need to have a good idea of especially sine and cosine. What do they look like? How do we manipulate them? So that's what this section is about. Put it on a fresh page here. 5.3 trigonometric graphs. Okay. So in this section, we focus on sine and cosine. Okay. And then we'll see if we can get to the other functions. I mean, we can always use Desmos if you're not sure. So we can always use Desmos to graph other trig functions. So that's kind of where we'll get to. So first things first, we already decided that, okay, we can go around the unit circle, right? So we've focused on the unit circle and we can just keep going and going and going. And what actually happens is we end up at the same terminal points. So we say sine and cosine are periodic because remember, sine is the y value on the terminal point and x is the cos, or cos is the x. So that's what we established. Oh, wait, that's from September. That's what, hey, what happened? Okay. It did end unexpectedly, okay. Back in action, I think. Okay. So, oh no. Oh no, no, no. Okay. Okay. Try to go slow. It doesn't want me to. Okay, it keeps telling me I have to reboot. So just a second. I'm gonna pause. So we'll pick it up here. So like I said, at the beginning, right, we've got this essentially a terminal point, right? X, y. So if we know that x is cos and y is sine, well, if we're moving around the circle, right, we're gonna get back to the same point. My technology is failing me today. I think we're back. Okay, good. Maybe it didn't like me going like this. Right, so we're moving around the circle, and what happens is we get back to where we started. So we're just going to move around and around the circle, and what happens is we call cos and sine periodic functions because they go around the circle. Okay. Hopefully it'll keep up here. So we say that the function sine and cosine have a period of 2 pi. Remember, the circumference of the circle was 2 pi, or of the unit circle, right? Circumference of the unit circle is 2 pi, right? So if you think about your unit circle here, let's see, if I go to this point, xy, right? And then I go around 2 pi, I get back to the same place, right? And so that's what makes these periodic functions, and the period is how long it takes to get back to where you started. So the period, maybe I'll scoot this over a little bit. The period is how long it takes to get back to where you started. Okay. So if we think about sine and cosine specifically as if they're y and x, right? Sine is y, cos is x. It gets confusing for me because I always talk about x and y in that order, but then I talk about sine and cosine. Anyways, just remember which one's which. Okay. What we can do is we can list, so for each value of t, right, we have some cutoff points. We have a lot of cutoff points that we already know, right? We know the quarter way marks around the unit circle, but we also know pi over 6 and kind of multiples of pi over 6, pi over 4, pi over 3, and then pi over 2, and then we keep going, but then we just replicate those points for each of the quadrants, right? And so what happens is we can go through, let's see here. We can go through, let's put that there. And we can say, okay, up here we have our t values, right? Our t is the distance on the circle, and our sine t is going to be our y value, right? So at pi over 6, we know that the terminal point is at root 3 over 2, 1/2, right? Let's see if I brought that. I did not. Okay, that's okay. Right, because here, let's just refresh our memories on these points. Remember, you only need the first quadrant, and then you can just remember where x is positive and negative and where y is positive and negative. And then we replicate all these points in each of the quadrants. So here we've got pi over 6, pi over 4 is the halfway mark, and then pi over 3. And here we've got pi over 2. Here we're at pi. And here we're at 3 pi over 2. And then here we're back to, 0 or 2 pi. Okay. So at pi over 6, right, we know that the point is at root 3 over 2, 1/2. And then pi over 3, while I've got it, right, is just the reverse. So this is at 1/2 root 3 over 2. Right? Do your best to memorize these. It's going to really pay off. So whatever you need to do to kind of remember, pi over 4 is pretty easy. Root 2 over 2. Oops. Root 2 over 2. Hopefully I didn't muck those up. And then pi over 2 is at when x is 0, y is 1. Here we started at 1, 0, negative 1, 0, and 0, negative 1. Okay. So what's happened here is, okay, when t is 0, that means we've moved nothing, right? At this point, x is 1, so that's your cosine, and y is 0, so that's your sine. That's going to help you remember where these functions start, right, on the graph. If you've ever graphed any trig functions, you know that one starts at 1 and one starts at 0, but they have the same shape, right? Even though we haven't seen these functions, I do kind of assume that you've seen sine and cosine at some point before. So here, right, this is your cos t and this is your sine t. Oops. Right? And so here is your cos t, and here is your sine t, right? So remember, cos is your x and sine is your y. So what does that mean? Well, the sine of pi over 6 must be 1/2, right? The cos of 1 over, or pi, sorry, pi over 6, not 1 over 6, pi over 6 is root 3 over 2, right? And so we can go through, notice we haven't even included the pi over 4 cutoff point because we get a pretty good idea of what's going on here just with pi over 6 and pi over 3, and then we go through to pi over 2. So what's going on here is here you've got your first quadrant, your second quadrant, right? So let's have a look here. I'll just highlight this. I'm gonna move this down just a smidge. Okay. So here, this is your quadrant 1. X and Y are both positive. Here's your quadrant 2. X is negative, Y is positive in quadrant 2, we know that. Okay, and that's reflected here, right? Cosine, both of those cos of 2 pi over 3 and 5 pi over 6 are both negative, right? So your x values are negative and your y values are positive, so sine is positive. If we keep going, we get through Q3, and then finally Q4, right? So what happens is we're just looping through the circle, right? And then once we hit 2 pi, we're back to where we started. Okay? So what this means is that we notice that sine t, sine of 0 equals 0, and cos of 0 equals 1. Okay? So these tell us our starting points for sine and cosine. So these will be our, I'll put it in quotes, starting points for sine and cosine. Okay, so let's have a look at some of these graphs. Oh, I need to, hey Jared, can you come grab this? Just a second. It's the end of my disruptions today. Can't even think of the word. All right, so we've got the graphs of sine and cosine. Let's look at sine first. Okay, oh, let's do it even bigger actually. Okay, so here, what we can do is, okay, knowing that at 0, right, so when t is 0, which we can actually translate to x being 0, which is confusing, right, because we've got x, y coordinates, but now when we flatten this out, what you'll see is you've got your x-axis, right, but you would still be talking about the sine of 0, right, so the sine of 0 is 0, so sine starts here at the origin, right? And then what we can do is, as we're moving through, so here we're in the first quadrant, right? And then we move through the second quadrant, and now our values become negative, right? So now we're in the third quadrant, and then we move on to the fourth quadrant, and then we cycle back, right? So that's why we say that sine has a period of 2 pi, because it takes us 2 pi, a distance of 2 pi to get through that, a full cycle. Okay? So sine t starts at the origin, 0, 0, since sine of 0 equals 0. Okay? And it takes a distance of 2 pi to complete one cycle. So we can do the same thing with cosine, remembering that cos of 0 is 1. So now let's have a look at what that means for the graph. Cos of 0, so here at 0, is 1. So now we're starting up at 1. And then what happens is we go through and we move through. So here, quadrant 1, quadrant 2, quadrant 3, quadrant 4. It still takes us a distance of 2 pi to cover the whole cycle, right? But another thing that we'll notice or start to notice is that sine and cosine only go between 1 and -1, right? But that's because we're moving on the unit circle, right? So we only go and we kind of cycle between 1 and -1. And depending on if we're talking about sine or cosine, we'll either start at 0 or 1. And of course, we can manipulate these functions. We can flip them, we can stretch them, but at their core, they have this, this shape. So like I said, we can manipulate these graphs, and it's going to be really useful to know kind of how they get manipulated. Oops. So the sine and cosine curves, general sine curve A sine k times x minus b, and y, which is a cos k of x minus b, as long as k is greater than 0, we say have an amplitude of the absolute value of a. Notice that a here is just multiplying the sine or the cosine, and let's just compare these. The only difference here is that this is sine and this is cosine. So everything else is the same. It's just the function that you're starting with depends on what's in there. So a gives us the amplitude. In fact, the amplitude is the absolute value of a. So even if it's negative, you just take the absolute value. So you essentially drop the negative. So the amplitude is the absolute value of a. So I'll just say here, drop the negative. We know that's not what actually happens, right? Negative values, you take the negative value of x, it's a piecewise defined function, but for us, we can just think about it as dropping the negative. So I'll show you what the amplitude is in a little bit, but the amplitude is just essentially a stretch. Okay? So, which we kind of, you might know from maybe some sort of physics course, right? The amplitude is just kind of how big your movement is. The period is 2 pi over k. Now that's a little bit weird, right? It's going to be 2 pi over k, where k gets pulled from how we've arranged our sine and cosine functions, right? So it's just multiplying our x minus b. Notice that x has to be alone. So this is similar to when we had to write our quadratics in standard form, right? But without the work. So we might have to rearrange our sine or cosine functions a little bit to make it look like this, right? But in general, we can just pull it from how the sine or the cosine functions are written. We can also have a horizontal shift. which is just going to be b. Notice that you have x minus b. b in x minus b. So x plus 3 means that b must be negative 3. Oops. Right? We've seen that that type of thing before when we were dealing with quadratics, right? And so just remember that it's x minus b. So if you have x plus a number, then b must be negative, right? Making a negative horizontal shift. Okie dokie. So let's do just an example here. We'll come back to this, but we'll start with just the amplitude and the period, so we can focus on them. Okay. Let's do 21. We have to find the amplitude, the period, and the period of the function and sketch its graph. Oh, you know what? I forgot. The graph wasn't very good. How am I going to put this? I'll do a graph over here. I'll do the sine curve or a sine curve. Whee. Oh, should go 2 down. Symmetric. This distance here, so from the x-axis up to here, this is the amplitude. I realized I hadn't shown you guys. Doesn't quite read amplitude, it reads amplitude. Yeah. So it's only the portion, so it's essentially half the height. So we need to know that if we're going to graph this thing, right? And we're just sketching graphs here. So for 21, we've got y equals negative sine 3x. So what we first have to do is we have to rewrite this. So I've got a sine function, and so I need to rewrite it in terms of sine like this. So here I'm going to just copy. Oops. There. Okay. I have something multiplying our sine, -1, fine. I also have something multiplying x, and then we see that x minus b must be 0, so b must be 0. So what we're going to do is we're just going to rewrite this as -1 sine 3 times x minus 0, right, to make it match the default one, the standard form, if you will, so that I can look and see what k is, what b is, what a is. Okay. So here I've got a is -1, k is 3, and b is 0. So now I can say that my amplitude is the absolute value of a, which is the absolute value of -1, which is 1. And my period's a little bit weird, right? 2 pi over k, where k is 3 in this case. 2 pi over k, which is 2 pi over 3. I can't really simplify that. That's okay. Right, so my period now is 2 pi over 3. So what happens? 2 pi over 3, if the, just in general, the sine period has 2 pi, right? So it takes me a distance of 2 pi to get through a whole cycle. Now it takes me a distance of 2 pi over 3. that's a little bit faster, right? So so it means that I'm just going a little bit faster, 2 pi over 3 instead of 2 pi to cover a full cycle. Okay. And let's see here. My third is the horizontal shift is none. Horizontal shift is B, which is 0. And I'll line this up here. Okay. So what I've got, if I have to sketch this thing, right? The period is 2 pi over 3. A little bit tricky because what I want to do is I want to break it up into quarters, right? And so because I know if I have to now and sketch its graph, okay, because I know how it behaves, right? I know that if I know the starting point, then for the sine, oh, sorry, this is cosine, sine, right? I start here at 0, 0. If I have had a shift, right, a horizontal shift, then I would need to move my point over. I haven't. I have a horizontal shift of 0, so I start at 0, 0 still. But then instead of taking 2 pi to move this whole distance, it takes me 2 pi over 3. So I've shortened this distance, so this whole thing gets smushed up, right? The amplitude we found is still 1. So the height from the x-axis to the top here is still going to be 1. So it's not getting elongated, it's just getting smushed together. Okay. So let's say this is at 1 and this is at -1. Okay. And it takes me a distance of 2 pi over 3 to get back to where I started. And there's no horizontal shift, so I'm starting here and I'm ending here. I'll still cross the x-axis, but I'm going to start heading up this way, and then at some point I'm going to start heading down, cross over, down, and then up again, right? Because we know we've got that general shape, right? So let's have a look in Desmos to see what's going on here, because I want you to graph these things, but at the end of the day, you can just use Desmos, and because figuring out where these breaks are, right, can be difficult, right? But you just do 2 pi over 3 divided by 4, right? You break it into quadrants. But let's see. Hopefully my screen share sticks around. Okay, so in our functions, over on the right-hand side, you've got your functions. And so now we can do something like, was it negative sine? Negative sine of 3x, I want to say. Okay. So notice we start at 0, 0, and it even gives us, oops, the cutoff points, really nice in exact form. Okay. So it's going to, right, it's starting at 0, 0. Oh, I forgot. Negative sign means it's flipped. We're not going to do that though. Was it negative sign? I picked a hard one. That's okay. Negative sign, just we know what negative, the negative of a function is. We just take all our y values and make them negative. So it actually flips here. Look at this. Starts going up again. Let's erase these. There. since the sine function is negative, pi over 6, pi over 2, and then 2 pi over 3. But notice the height, right? The amplitude is 1, and then it goes down to -1 because it's the same, right? So let's just copy those cutoff points. Pi over 6. So here, this is going to be at pi over 6. This is going to happen at, is it pi over 2? Sorry, pi over 3 and pi over 2. And then 2 pi over 3. Oh. This doesn't look like a 6. Still probably doesn't. Yeah. And then the height, the amplitude here is 1. Let's do one, but we're not going to sketch these because I'm not going to be able to make you sketch on a test. If you're sketching in real life, you'll have Desmos, so I just don't really see the point. So what I want to do is I want to start talking about the horizontal shifts. So in the next set of questions, right, we were going to find the amplitude, the period, and the horizontal shift, and then we're ignoring vertical shifts and just kind of negative flips and stuff like that. So I don't want you to graph it. I just want you to figure out what the amplitude, the period, and the horizontal shift are. So let's do, I'll leave the first few because they're pretty easy, right? Especially if we're not graphing them, but graph them in Desmos. Graph in Desmos instead, right? To make sure that what you found is correct, right? To check your work. So how about we do a kind of a weird looking one? Let's do 40 together, right? Like I said, sometimes we have to rearrange things and kind of morph them to become that standard form, or what I'm calling standard form. Because it looks very similar to the other standard form. So if we have y is 2 sine 2 over 3x minus pi over 6. Okay. We want to morph it into this little guy. Rewrite in this form. Right, and I'll use the highlight that I have here, the sine and the sine. So that's why we're going to rewrite it like that. Hi, cutie, how are you feeling? So y, there's nothing I need to do with the 2 out here in front. That's just going to be my a, okay? But I do need to shake the x loose, right? So that means I need to pull out a common 2 over 3 out of 2 over 3x as well as minus pi over 6. So what I have is I get 2 sine, and then I'm going to just show the 2/3 pulled out before I actually pull it outside. Minus, and here's where I'm going to get a little bit sidetracked here. Maybe up here. Pi over 6 divided by 2/3. We know from dividing fractions, right? That's pi over 6 times 3/2. So then I get 3 pi over 6 times 2, 12, which I can just reduce to pi over 4. So here, this becomes 2/3, 2/3 times pi over 4. Notice the 2 would cancel with one of these 2's and 4's. So then we have pi over 3 times 2, which is pi over 6. So we haven't actually changed anything, but I need to extract that 2/3. Right, so now I have a common 2/3. So now I can pull those outside to make k, right? Because inside I can only have x minus something or x plus something if b is negative, right? And so I need to pull out that 2/3 because that's what's attached to the x. So now I have y equals 2 sine 2/3 times x minus pi over 4. Okay. All of a sudden, it's easy to see what the amplitude is, what k is. K isn't the period is 2 pi over k, right? So we'll need to find that. But the horizontal shift is pi over 4. So the amplitude is the absolute value of A, which is 2 in this case, the period, and a lot of people kind of forget that it's 2 pi over k and just want to write k, but it's actually 2 pi over k, which is 2 pi over 2/3, which if we're thinking about our fractions, right, that's 2 pi over 1 times 3/2. That looks like 3 pi to me, right? If I cancel this 2 with this 2, I get a period of 3 pi. Thinking about our regular period, right, just a standard sine curve, a standard sine curve has a period of 2 pi. Now I've made it 3 pi, so it's a little bit longer, so it's kind of stretched out a little bit. Okay. And let's see here. Oh yeah, the horizontal shift, I'll put it here so I'm not taking up a ton of space, is B, which in this case is pi over 4. Okay? Meaning we've shifted this whole thing, the sine curve, over pi over 4 units. Okay. Shift the starting point over by pi over 4. And then I'll say to the right, right? Because it's positive, so you're going to shift in the positive direction. It's one of those confusing things, right? If you've got x minus pi over 4, at least I want to shift it to the left, but it actually shifts it to the right. To the right. Okay, so let's see here, the amplitude, right? Our min and our max values should be at plus minus 2 then, right? Because now from the x-axis, I'm going up a height of 2, but I know that I'm going to fluctuate between these two values, right? Plus minus 2. And the period is 3 pi. And so a full cycle happens in a distance of 3 pi. Notice, right, that's 3 pi from pi over 4. Okay, so when we're looking at our Desmos graph, right, we're going to use Desmos to check our work. I need to remember that from pi over 4, the cycle should take 3 pi to finish. From the starting point of pi over 4. So let's go to Desmos and see what's going on here. Oh, did I copy down? Do I have it? I do. Okay, so I've got 2 sine, 2 divided by 3, and I'm going to step it up, x minus, and then I want pi, which there is a button here, pi divided by 6. So just make sure that your function that you're writing out actually matches the one that you started with. Or if you want to, you can do the one that you started with, so the initial one that you're given, as well as the one that you transformed, right? When we pulled out that 2 over 3 from the x and the pi over 6, we ended up at, so let's just make sure that we didn't change our function, right? Because that's always a good start. 2 times the sine of 2 over 3, and then I'll do a bracket times, how do I do it? In Desmos, I didn't even try it. Sine 2 over, you know what, I'm gonna do 2 brackets. Because what am I trying to accomplish here? Times x, okay. I have to keep the x minus pi over 4 inside the sign, right? But I've also pulled out that 2 over 3. And so what I can do is I can just rewrite this as x minus pi divided by 4. End that bracket, and then end that sign bracket, and phew, it looks like these are the exact same function. But it also helped in teaching me how to write things in Desmos. So notice that the sign has brackets all around it, and then I've pulled out my k in brackets, and then I've got my x minus b in another set of brackets. Those last set of brackets aren't really necessary, but it helps to show it off. Okay, so we managed to transform our function to match the original function. That's a job well done on its own. Okay, sine, remember sine starts at 0, 0, right? Sine of 0 is 0. And so here we had a horizontal shift of pi over 4. Okay, so now we're starting at pi over 4, and we've got an amplitude of 2. Right, so we're going up 2, and then let's see if I can zoom this out a little bit. These check-in points, right? So if we did pi over 4 plus 3 pi, which is the period, right, we should end up at 13 pi over 4. So it takes us a distance from pi over 4 to 13 pi over 4 to cover that whole cycle. Okay. And notice, yeah, we're bouncing between positive 2 and negative 2. Okay. So I don't know why I opened that, this one. In Desmos, to enter y equals 2 sine 2 over 3x minus pi over 4. Oops, a little hang up. Right, 2 sine bracket 2 over 3 bracket x minus pi over 4 bracket bracket. Okay, because all this must be inside the sine function. Okay. Let's do one more, and then we'll move on to the next section. Let's do a cosine. I want to do a positive one, so let's do 42. Y is 1 plus the cosine of 3x, 3x plus pi over 2. I just want to make sure I got that. 3x plus pi over 2, good. So now I've got a cosine. I've also got this 1 plus the cosine, so that would shift this whole thing up by 1. We're ignoring that. We're only asked to find the amplitude, the period, and the horizontal shift. But that is something that we would do and we will see when we graph it in Desmos. Okay? But that's just in general how functions behave, right? If I'm adding something to the function, it's a vertical shift. Okay, so what I need to do is I need to rewrite this. It's a cosine function, so I'm going to go and grab that default cosine function, and then I'm going to rearrange it until it matches. Copy. Oh, did it again. There we go. Okay. So I need to rearrange it so I have x minus b again, right? Which means to get x on its own, I have to pull out a common 3. So I need to pull out and extract that 3, which also means that my k is going to be 3. But I need to pull it out of pi over 2. So we need to extract a common 3. Okay, so from 3x, that's fine, we just divide out the 3. From pi over 2, we need to do a little bit more work, right? So what we're doing is pi over 2 divided by 3 over 1, essentially, right? Puts me at pi over 2 times 1 over 3, which is going to be pi over 6. Okay. So now I can rewrite this as y equals 1 plus the cosine of 3 times x plus pi over 6, right? It's positive. Nothing's changed. I pulled out a positive 3, so it's going to be plus pi over 6. That changes some things because now we've got a shift to the left, right? Because it's x minus b here. So my b must be negative pi over 6. So let's just highlight what we've got here. K is 1. K is 3. And b is negative pi over 6. Okay. So once you rearrange things, it's really easy to see what the a and the k and the b are. Okay. This makes a vertical shift up 1, right? But we're ignoring that because all we're asked to find is the amplitude is the absolute value of a, which is 1. The absolute value of 1 is 1. The period is 2 pi over k. And don't forget it's 2 pi over k. So we get 2 pi over 3. And then the horizontal shift, is b, which is negative pi over 6. So because it's negative, right, it's to the left. Knowing that we started with a cosine function, right, where we start this thing, well, the cosine of 0 is 1, right? The x at 0, at an angle of 0 is 1. And so we start up top at 1, but now we've shifted to the left pi over 6, so that starting point has shifted over. And then we've got that, the vertical shift of 1. So I'm expecting to see the starting point at negative pi over 6, 2. Let's make sure that that's what actually happened. So I'm just going to use the initial function that we were given, 1 plus, and then the cosine of 3x plus pi over 2. Okay. Right? So why am I so relieved? Because what I said was true. I've shifted a horizontal shift of negative pi over 6, fine, because I started at 0, 1. And then because I started at 0, 1, and then I had a vertical shift up 1, then this initial point must be at negative pi over 6, 2. Okay? And then what we do, we can go through and we can find all the points in a cycle. And it even shows us more points on the cycle or in the on the function, but usually we just graph one function or one cycle. Cycle. Okay. So just get comfortable manipulating the sine and the cosine functions and making them look something like this. And then it's easy to see what the amplitude, the period, and the horizontal shift are. Okay. So we'll leave that behind and start talking about in chapter 6. Now, chapter 6 goes through and does exactly what we just did in chapter 5, but with a slightly different approach. So a lot of this stuff is going to sound familiar. It is familiar. You know it already. It's just taking a slightly different approach with the special triangles. Now, for the most part, you'll be able to stick with one approach or the other. You don't have to know both. But there are some instances where one is a lot more helpful than the other. So we need to start by talking about radians. So we've already talked about radians in terms of on our calculator, we have to be in radian mode. Okay, fine. We didn't really know why. Right, but I'll bring this in and on a new page, I'll start. So 6.1, what was it called? Angle measure. Okay. So what we have is, let's talk about what a radian is. And this graph is gonna help. Okay. I think I snuck it in once or twice, but we talked about we talked about angles, right? We haven't called them that, but pi over 6, pi over 4, pi over 3, pi over 2. Okay, so they're just going to be the distances on the circle. Right here it's confusing because we didn't start at 1, 0, but that doesn't matter. A radian measure is just the distance on the circumference. So if a circle of radius 1 is drawn with a vertex of an angle at its center, then the measure of this angle, okay, so here in the middle here, in radians, is the length of the arc that subtends the angle. Okay, so going from here to here, right, we've talked about things like, and it's even in the notes, so I'm going to grab it there. We've already talked about some common angles here, right? Pi, radians, let's talk about these middle two, right? Because these we already know and we've seen. We have seen these earlier. Okay. So what happens, okay, so if we've got some sort of angle here in the middle, then the distance of the length of the arc that subtends the angle, well, really where we started to where we ended, which is a terminal point, right, is going to be, so this distance is the radians. So it gets a little bit confusing, right, because we talk about this as the angle, but also the distance on the circle as the angle. But if you think about it, they're definitely related, right? And so that's what radians are. So pi radians, well, that's just the distance from our starting point here and halfway through. Oh man, got another call. Is insane. Okay. It's so funny because I don't actually teach that much. I mean, Tuesdays and Thursdays I teach for 4 hours straight. But honestly, the number of phone calls and just kind of weird stuff that happens during class, I don't know where it's coming from. I don't know. I can't explain it. It's like people know what I'm teaching. Even yesterday's, like on Mondays, I teach from 3 to 5 here. And so for some reason, that's when I got all my phone calls. It's weird. Anyways, it's annoying. So we've seen these and we know where we end up if we go pi over 2 radians. Well, I know that that's a quarter of my unit circle, right? Things I don't know are things like 2 radians. Well, 2, okay, pi over 2, if you convert it to a number, right? You can still convert it to a number because pi is a number. Pi divided by 2 is actually 1.57. Okay, so then here we've gone 1.570796 radians, right? So if we want to go 2 radians, so no pi's involved, actually makes it harder. We go a little bit further, right? 1 radian here, right? A full distance around would be 2 pi radians, right? Because that's the whole distance around the circle. So we know a lot of these radians already, right? And especially those cutoff points, pi over 6, pi over 4, pi over 3, pi over 2, right? We know all those. We're going to start talking about degrees, which is probably what you're more comfortable with, right? We know things like halfway around a circle. If I've turned around, I've gone 180 degrees. If I've done a full turnaround circle, then I've gone 360 degrees. So usually we're more comfortable with degrees than with radians. And of course they're related. So a right angle is a 90-degree angle, right? Half of that is 45 degrees. And so we can make that connection between radians and degrees, notice that we said before, right? If we have degrees, we have to show it with this this degree symbol, right? If there are no units, you're in radians, right? If there is a unit, this specifically this degree, then you need to be in degree mode on your calculator. So 180 degrees is pi radians. We already established that up here. 180, we probably know already, is halfway around a circle. And so 180 degrees is pi radians, which means that 1 radian is 180 over pi degrees. That's not that easy. So to convert degrees to radians, multiply by pi over 180. That's actually relating to this one here. And then to convert radians to degrees, multiply by 180 over pi. So let's do a couple of examples so that we can move back and forth between these two. I actually think it's only from radians to degrees. I didn't grab any more, but that's okay. Remembering, right, that a negative angle just means that you're going clockwise instead of counterclockwise. That's the same for radians, degrees, anything, any measure, any angle is going to be positive, counterclockwise, negative, clockwise. Let's do 18 first. So we've got 3 pi over 4, which we want to convert to degrees. Okay. To convert degrees to radians, that's not what we want, right? To convert radians to degrees, multiply by 180 over pi. Okay. And so we have 3 pi over 4 multiplied by 180 over pi. Okay. Notice that the pi's cancel, right? And because they're exactly equal, I'm allowed to do that. And then I've got 3 times 180 over 4. Let's see if 180 easily divides by 4. It does. Becomes 45. So 3 times 45 is 135. Degrees, 135 degrees. Remember to use the degree symbol for degree angles or degree measures. Okay. How about, what if we did 28, right? It's a negative angle. That doesn't actually matter, right? Because I'm just going to keep that negative on the outside because it's just telling me the direction that I'm going. And then I'm just going to deal with the 13 pi over 12. So I've got negative 13 pi over 12. And so this is just saying go clockwise. So I'm not going to worry about it. It would just translate, right? Because all I need to do is say, okay, well, 1 degree is pi over 180 radians. So each radian is going to be multiplied by pi over, I'm going backwards. Like, hey, that doesn't work. Each radian becomes 180 over pi degrees. I actually find these easier to follow than these ones. For some reason, they don't click for me. That's okay. Survived. So to convert radians to degrees, multiply by 180 over pi. This one here, and then degrees. So times 180 over pi. Pi's will cancel. 180, I'm just going to see if it divides nicely by 12. If it does, it does. 180 divided by 12 is 15. So what I get is I get negative 13 times 15, which is negative 195 degrees, right? So that's 195 degrees clockwise. 195 degrees clockwise. Good. Okay. We've sort of, and there's a note here, when no unit is given, the angle is assumed to be measured in radians, right? So that's important to remember. We've talked about standard position, even though we weren't talking about angles necessarily, right? But we always start here on the positive x-axis, and then our angles are measured from there, right? And so here, steal this little graph here. So here, this is the standard position. Okay. So all our angles are measured from that point, right? So here in the A, you've got this just a positive angle in the first quadrant. And here, again, you've got a positive angle, but notice that you end up at the same spot, okay? Means that they're coterminal, which we've sort of talked about before, where you end up, if you end up at the same terminal point on the unit circle, then we say that they're coterminal. So here, A and C are what we call coterminal, and maybe I'll scoot this over a bit. And fill that in. So A and C end up at the same terminal points. So we say they are coterminal. Right. Even in D, if you go one loop around, two loops around, we've done that, right? It just loops us around the circle until we get to that point, right? So we just take away 2 pi, right, or 360 degrees until we're down to the core circle. If that makes sense. Okay. Let's see here. Let's do just one of these. Seeing if two angles are coterminal, meaning they just have the same kind of core angle, right? Okay. So we're dealing a lot with degrees. Notice that if it has a degree mark, then of course we're working in degrees. Whereas if you've got a pi or just a flat number, no units, then you're working in radians. So just here, note that here you're in radians, here you're in degrees. Especially if I asked you to take the sign of each of these, right? You would have to change your mode on your calculator from degrees to radians and back and forth, right? So Let's start with 37, just because that's what we've been doing so far, right? 37. We've got 5 pi over 6 and 17 pi over 6. There. We can draw our 5 pi over 6, right? If we went, so here, this kind of takes us back to, all right, our reference numbers, right, would be pi over 6 in the second quadrant, right? So here I can draw, maybe I'll do it nice and big here. So if I have my unit circle here, and 6 pi over 6, how do I know I'm in quadrant 2? Well, because 6 pi over 6 would be pi, right? So I can make a little note here that this is at 6 pi over 6. So then if I split this up, I know here I'm at pi over 6. 2 pi over 6 puts me here. Oops. 3 pi over 6 is here, right? Pi over 2. And then 4 pi over 6, 5 pi over 6. Okay. So this first angle here, 5 pi over 6, remember radians is just the distance that subtends the angle. So what we can do is we can start here in the middle, and starting from this arm here, our angle 5 pi over 6, we can actually draw like this. So now what we do is we show that it's an angle with a little loop in the middle to show, okay, this is an angle, and this angle is 5 pi over 6. Okay. Because this point is not 5 pi over 6, that's the distance that we've traveled, but now we're morphing it into saying, okay, well, the distance that we've traveled is actually the radians, which is an angle measure. I know where I end up here. I end up at 5 pi over 6. My reference angle is pi over 6. X is negative, Y is positive. So here, just for kind of practice, my at pi over 6, I'm at what point? Root 3 over 2, 1/2. So now X is negative, negative root 3 over 2, and Y is positive 1/2. Right? That's from the last section, but they're all hanging together, right? So now we want 17 pi over 6. 17 pi over 6, I just need to figure out, okay, well, it seems like I've looped around some number of times, right? So 17 pi over 6. 17 pi over 6, we can rewrite as, well, 2 pi, I know a distance of 2 pi is 12 pi over 6, right? Is 12 pi over 6 plus, well, 12 taken away from 17 puts me at 5 pi over 6. Right. Here's the first loop, one loop, and then here's the actual distance that I've traveled in terms of my angle. So here, I can go one loop around. Oops. Should go like that. That's going to be 17 pi over 6. So, looks like they end up at the same point, right? 5 pi over 6. A loop and 5 pi over 6, they are coterminal. Okay. So, since we end up at the same point, oops. I always want to combine words when I write them. At the same point, these angles are coterminal. So we know how to deal with radians, and that's the hard part, right? So let's have a look at maybe 40. Now we're in degrees. So 40 was 50 degrees and 340 degrees. Okay. So already I have a pretty good idea of what's going on here because we have such a good kind of grasp on degrees, right? And so here, what I can do, but we apply the same idea, right? Let's start with the 340 because that's the easiest one that I see, right? So 340, well, if I go up the full distance around the circle, I've gone 360. So I'm just going to leave a distance of 20 degrees, even though I don't know what a distance of 20 degrees might look like. I think it's pretty short because, well, let me think about this, right? 90 degrees, I know that's 90 degrees just from life, right? This is 180, and then 180 plus 90 puts me at 270. So here, I can talk about, well, this is 90. Oh, sorry, I write 60, but I said 90. Here's another 90, so that's 180. +90 plus 90 plus 90 is 270. And then here would be 360. So I'm going to end up going from here to here, let's say. So this is going to be 340 degrees, where, of course, my reference angle would be 20 degrees, right? And so here, this angle, 340 degrees, going counterclockwise because it's positive, 340 degrees, puts me 20 degrees below the x-axis, below the positive x-axis. So even though I don't know angles or, degrees that, that well from life, we can figure out where 340 is roughly, okay? How about 50 degrees? Well, I know if this whole distance is 90 and halfway there is 45, then I'm just a little past the halfway mark. So probably something like this, right? I'm just kind of putting in my markers of things I know. Oops, 45, right? Then that distance must be 50 degrees. So these are not coterminal, right? Because they don't end up at the same place. So therefore, 50 degrees and 340 degrees are not coterminal. Okay. Good. So we kind of tackled the hard part of trig, I'd say last week when we did 5.1, 5.2, kind of establishing all those rules. And then now we're going to use the right angles. So now we're going to use this familiar SOHCAHTOA to solve these problems, right? So we've got a classic triangle here. And what you'll find is that we've got two special triangles that we need to keep track of. And as long as you're able to know these, that's the equivalent of our pi/6, pi/4, pi/3 cutoff points. Okay. So section 6.2, I think. Let me just make sure. Trigonometry of right angles. So here, right, this is the same, so sine, cosecant, cosine, secant. Notice that cosecant is just 1 over sine, right? So they've been flipped. Right? Recall from high school, probably. SOHCAHTOA. Oops. Everyone kind of remembers SOHCAHTOA, I think. What does it say? It says sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tan is the opposite over adjacent. So as long as we keep track of which is the opposite and the adjacent and the hypotenuse, then we've got a pretty good handle on the first 3. And then knowing that the other 3 are the inverses makes it easy, right? But those we have from the previous sections. So here, this is saying that sine theta, theta is just going to be some angle. So theta is an angle, right? We've been using t a lot, but theta, t, theta, you can kind of see the connection there. So theta is an angle. It's just a variable that we use for angles a lot of the time. So sine theta is the opposite over the hypotenuse, where sine opposite hypotenuse, right? And then cosine, cos theta is adjacent over hypotenuse. And then tan theta is the opposite over adjacent. Right? Which means we need to keep track of, well, which is which here. Hopefully it's been drilled into you already. Right? So here, if we've got some theta here, so theta is some angle, then the side that's opposite that angle is, of course, the opposite. The length, so the longest side, which is also the side opposite the right angle, is called the hypotenuse. And the adjacent is the shorter side. So the hypotenuse is the longest side, and the adjacent is the shorter side that's attached to theta. Okay. So knowing these 3 sides, right? I can find sine theta, I can find cos theta, I can find tan theta. I can even find cosecant, secant, and cotangent. Okay. So what I'll say here is that if we know the lengths of all 3 sides, we can easily solve for the 6 trig functions of theta. We can easily solve for the 6 trig functions of theta, right? And what I mean by that is sine theta, cos theta, tan theta, cosecant, secant, and cotangent. Of course, you're going to want to have this handy, right? But then if you have all three sides, then you can just rearrange them, right? So hopefully I grabbed, yeah, example. So here in one of these, which one should we do? Okay, well, what's nice about the first two is that we actually have the length of all three sides. I want to do, let's do 6 maybe, just because one of the sides is missing. Okay? But we can find that, right? Yeah. Find the exact values, so you're not gonna simplify, or you can simplify a little bit, but you're not gonna find the approximate, the decimal approximation, right? You just want exact values. So find the exact values of the 6 trig ratios of the angle theta in the triangle. So for 6, oops, we've got something like this. Whee. Here, this square means it's a right angle, which is 90 degrees, or pi over 2 if you want. Okay. We're given that this angle is going to be theta. This distance is 8 and this distance is 15. Okay. We use the Pythagorean theorem that a squared, here, let's say, we know a squared plus b squared equals c squared, where c squared is the hypotenuse, or c is the hypotenuse. Hypotenuse equals c. So it doesn't matter which one we make a and b, but it's the opposite and the adjacent, or the adjacent and the or the opposite. It doesn't matter as long as you make c the hypotenuse. So this distance is c, so we have to solve for c. Not bad, right? We have a, let's let a be 8. Doesn't matter, you could make it 15. Notice 8 squared plus 15 squared is the same as 15 squared plus 8 squared. So we have 8 squared plus 15 squared is c squared. Okay. 8 squared is 64. 15 squared is 225, which is c squared. So 225 plus 64, 289. So c is the square root, I don't need that 2 there, of 289. It's the plus and the minus, but because the distance has to be positive, but distance is positive, right? You can kind of ignore it. So the square root of 289 is 17. So c must be 17. That's not always going to be nice and beautiful like that. So c equals 17, we solve for that. So like I said, now if we know the lengths of all 3 sides, we can easily solve for the 6 trig functions, which is what we want to do here. So now that I have these 3 sides, a little bit of work, not bad, I can figure out what each of these functions are. So I'm just going to steal this, copy, and paste. So here I need to keep track of which is my opposite and which is my adjacent and which is my hypotenuse. And so here, from theta, my opposite is 15. Adjacent, so the hypotenuse is 17. My adjacent then must be 8. And my hypotenuse is 17. Okay, so now what I can do is I can say sine theta must be, and I'm just pulling these numbers from up here, right? I'm just filling them in. Sine theta or SOHCAHTOA, you can SOHCAHTOA your way through the first three, right? And then just kind of reverse them for the last three. Or just follow this graph, it doesn't matter. Opposite over hypotenuse, so then here we can do all 6 really quickly. Sine theta is 15 over the hypotenuse, which is 17. Cos theta is the adjacent, which is 8 over the hypotenuse, 17. Tan theta is the opposite, 15 over adjacent, which is 8. Cosecant theta is the hypotenuse over the opposite, 17 over 15. Secant theta is the hypotenuse over adjacent, 17 over 8, and the cotangent theta is adjacent over the hypotenuse. Notice that these ones, they're just flipped, right? If the cosecant is 8 over 17, then the secant is 17 over 8. You'd have to remember that cosecant and secant are the ones that are related, but besides that, you kind of got it from the first row. All right. So not bad, right? As long as you're able to find all 3 sides, then you can solve for all of these trigonometric ratios. Okay. Are there any questions? I'll stop this here.